So today I'm going to present the ultrasonic signal noise reduction processing in borehole imaging application. This is the outline. First, I will introduce the background of the ultrasonic imaging so you can get general idea of its application. Then I will focus on the ultrasonic imaging system. I will talk about the pulse echo transducer. And next, I'll move on to the Ringdown Interference reduction method. Finally, I'll give you the conclusions and future work. So, borehole ultrasonic imaging provides 100% borehole coverage. I list several major applications here. For example, it can detect the fracture and provide fracture evaluation. This is critically important to the unconventional reservoir production. The first borehole televiewer operates at 1.35 MHz, and nowadays the modern tool operates at 250 kHz or 500 kHz. The reason we shift to the lower frequency because of the mud attenuation. And later in the presentation, I will show you how the mud attenuation can be, especially in the high frequency. Now, this is the typical wireline ultrasonic imaging system. We have the signal acquisition system on the surface to process the data, and the tool is connected to a cable, and the transducer is mounted in the tool, and the borehole is filled out with the fluid. So we lower the tool into the borehole until it reaches the bottom of the borehole and pulling up. While pulling up, the transducer is rotating, as shown in this figure. Typically, we are using pulse echo transducer in the ultrasonic imager. The transducer fires signal into the borehole and receives the echo reflected from the borehole wall. The received amplitude corresponds to the mud attenuation, borehole roughness, acoustic impedance, and fracture. If the transducer hits the fracture, a certain amount of energy can be lost, so we can distinguish fracture from the amplitude variation. As I said that we usually use the pulse echo transducer in the wireline imaging system. So the conventional pulse echo transducer applies the piezo ceramic element. It has good stability in the high temp, high pressure environment. It is also known for relatively weak output. In order to overcome this shortcoming, we developed an improved version of pulse echo transducer using the piezo composite element. So here I show you the 1D modeled pulse echo excitation signals and frequency responses of two 250 kHz transducer designs. Left figure is using the ceramic element. Right figure is from the composite element. And black lines are the waveforms, and they are the excitation echoes, and blue lines are the frequency responses. If we compare these two figures, we can see generally the composite transducer has almost 4 times of signal amplitude of signal and 1.3 times wider frequency band over the ceramic element. As a result, it provides the stronger returns and better dynamic range in attenuating mud and large standoff, which could provide us better image quality. Now let me show you the 2D beam field measurement. This is the laboratory measurement, and the transducer is in a circular shape, so it is symmetric in the lateral direction and elevation direction. And the z-axis represents the either lateral direction or elevation direction. Z-axis represents the in actual direction. So we have the near field, focal zone, and far field. The focal zone is from 40 mm to about 100 mm. This is our usable operation range. It's wide, and beyond 100 mm, that is far field, energy dies out, spread out quickly. And we try to avoid operation before 30 millimeter, because you can see there are double peaks, which also called as double edge effect. If we have target in this region, because of double peaks, it is difficult to distinguish to determine the position of the target. It could cause ambiguities. Now, I have introduced those good qualities of the composite transducer, and we are using it in our imaging tool right now. So I like to show you its performance by using a field example. This is from the 6.5-inch borehole. It's a pretty small borehole, and mud is the light-weighted water-based mud. X actually is azimuthal angle, Y actually is a depth. I ignore the depth here. So we see there is a large fracture, and this is the other borehole surface, borehole feature. And we have one group of fracture here, the other group of fracture here. So we can observe those small features. And we compare with the ceramic transducer, we see much better image. But on the background, we have problem that we observe this wood grain patterns. This is interference pattern. And on top of this wood grain pattern, we have the shading effect. If you compare these two blocks, this is dark and this is bright. This is the shading effect, which is low frequency noise. And what causes this wood grain pattern and the shading effect? We did a quick study, and we know this is due to the ring-down modulation effect. So first, I show you one synthetic example. I generate a synthetic ring-down noise, and which is blue line, and a synthetic echo, which is the red line. Then I'll assume the borehole, the tool is eccentric. So, okay, suppose I'm going to show you one animation here. That when the tool is moving, actually the echo is moving within the window, back and forth. But we have this ring down, which is blue line. It's relatively constant. So when the echo is moving back and forth, the ring down modulates the echo. What the transducer received is a composite signal of the ring down and echo. As a result, it's no more constant. So if we plot the peak amplitude versus the azimuthal angle, which is the position, so we can see oscillation curves. Now here it is symmetric because in our simulation the tool trajectory is symmetric. But in the real case, we also have mud in the borehole, and the mud is highly attenuated, as I said before. So now in this case, I add in the mud effect. Now you can see the amplitude of the echo is decreasing with longer offset. This is the received peak versus the azimuthal angle. So except for the oscillation, we also have the bias, low frequency bias. It is caused by the combination of the mud and eccentricity effect. Now, the above two examples are based on fixed eccentricity. In the real case, the eccentricity could be varying versus depth. Now, if I consider this into account, I can generate these two images. The first one is the leftist curve shows the tool trajectory. Y actually is the depth, X actually is the tool eccentricity. So you can see how the eccentricity is moving, and it is various versus depth. It's equivalent to that the tool is wobbling inside of the borehole. And this is the image. In this image, I did not consider the mud attenuation. Now, the right side, I consider the mud attenuation. Now, on both of these two images, we observe the wood grain pattern, which is very similar to the previous field example I showed. And moreover, when I consider mud effect, I duplicate the shading effect. So based on this previous analysis, we can draw a conclusion. First one is that the wood grain pattern is caused by the ringdown modulation effect. And the other conclusion is the shading effect is caused by the mud and eccentricity effect. So we have two issues here. In order to remove this or reduce this interference noise, we first apply the mud eccentricity correction. So we should have a look at the mud attenuation first. These are the lab measurements. We have two types of mud used in the field. One is the water-based mud. The other one is oil-based mud. Here I show you the attenuation versus frequency. So water-based mud has relatively less attenuation and less frequency dependent. So if you look at the attenuation over the frequency range, it is relatively constant. So in our processing, when we do the mud correction, we assume a constant factor. So correction for the for the water-based mud is relatively easier than the oil-based mud. The oil-based mud has this much stronger attenuation, and it is highly frequency dependent. So it is a much more complex case. In our study, we temporarily apply the attenuation at 250 kHz, which is also the center frequency of the transducer impulse. So after applying the correction, the shading effect can be reduced, so we apply the 2D median filter. 2D median filter is a low-pass nonlinear filter, which is well known for reducing the impulse noise. Impulse noise is high-frequency noise. If you look at the pattern, actually the wood grain pattern is a broadband signal. It covers low frequency and high frequency. So in our case, we assume those Borehole features as impulse noise. Consider them as impulse noise. Then we apply the median filter to first filter out these Borehole features in order to extract the most part of the background pattern. This is the output of this median filter. So most part of the background is extracted, but we still observe some sad effect. The middle part is over smoothing. If you look at the original image, actually the middle part is dominated by the high frequency. So this is one limitation of the median filter. Currently, we are developing one advanced filtering technique which can adaptively remove this interference pattern and will be covered in the future publication. So we do the image, back to this presentation, next we do the image subtraction. And this is the final result. Although we still have high frequency residual showing on the background, if you compare with the original image, we see significant improvement. Okay, now let's go back to the field example which I showed in the beginning. This is the original, this is a raw image, and this is the image after applying the mud eccentricity correction. So the shading effect is significantly reduced. And then we apply the median filter to further reduce the background pattern. So there is no Borehole features here. That is good. When we apply the image subtraction, that means the Borehole features can be preserved very well. And also if you look at the output of the median filter, it follows the trend of the wood grain pattern. To further evaluate its performance, we calculate the contrast noise ratio of these two images. The blue line is based on the original image. The red line is based on the image after processing. And here's the difference. So overall, if you look through the depth, generally speaking, the signal to noise ratio of the processed image is significantly improved. Okay, so I would like to move on to the last section, conclusions and future work. So I briefly talk about the piezo composite transducer, including the excitation functions and the frequency spectrum and beam field. After that, I move on to the processing method, which includes the borehole fluid attenuation eccentricity correction and median filter. And based on the field example, we can see the image contrast between the surface features and background are significantly improved. And also, I have mentioned that there is limitation of the median filter. It has limitations in filtering the high frequency noise. So we still have the noticeable residual left as background, and this residual is mainly high frequency noise. And last, I also mentioned that we are working on advanced image filter techniques on the images. This idea has done, and we have patented it, and will present work in the future publications. So finally, I want to give my thanks to Baker Hughes, and also thank the operators for the release of the data. So any questions?